Hey everybody, we will oh, we will start the lecture today, and we will continue on 4.4b. We will go deeper into this logarithmic function, and we will look at one big property of log function, that is that a log function is actually inverse of exponential function. Okay, let's call that a theorem instead. Yeah, theorem. If f(x) equals to log base a of x, uh, okay, earlier the connection was cut off a bit earlier. So the theorem, if a is positive and not 1, then the function fx a to the x has inverse function log base a of x. The proof, let a to be positive and not equals to 1. And fx equals to a to the x. Now then the process of getting the inverse, y equals to a to the x. Step 2, we swap x and y. Step 3, we change it into, we solve for y, right? So, and to do so, we change it into log form. And finally, f inverse x equals to log base a of x. So that's actually a very short proof. Not too hard, right? Not too hard. Okay, but let's see what this means. So with that theorem, so for example, suppose we say let fx equals to 2 to the x plus 3 minus 4 be the function, then find the inverse function. Then the solution, let fx equals to that function, step 1, y equals to 2 to the x plus 3 minus 4. Step 2, we swap the x and the y. So the procedure of doing inverse function, those 4 steps, should be something you get so used to already. Okay, and then x plus 4 equals to 2 to the y plus 3. So log base 2 of x plus 4, don't forget to use parentheses here because the log applies to x plus 4, equals to y plus 3. So y is equal to log base 2 of x plus 4 minus 3. Okay, and therefore step 4, f inverse x equals to log base 2 of x plus 4 minus 3. Okay, that's a little example about how to find inverse of exponential function. Of course, the exponential function has to be a one-to-one function first. If it is just a basic exponential function that we transform to the left, to the right, or stretch or shrink, then it's still one-to-one. Therefore, the inverse is still one-to-one. And that's actually one key ingredient for us to go on. Since exponential function is one-to-one, I should say the basic exponential function, because exponential function is one-to-one, then the inverse function is also one-to-one, which is a log function. Is also one-to-one. Okay, and because the inverse function is one-to-one, and we can use that property as the following. Log base a of blah equals to log base a of blah implies blah equals to blah. Okay, but with one restriction though. With a restriction, that both blah and blah are strictly positive. They have to be strictly positive. Why? Here's the reason. Why? Well, because the range of fx equals to a to the x is from 0 to infinity, right? Then it becomes also the domain of the inverse function. Let me call it gx now. Log base a of x is also 0 to infinity. Okay, so the domain of log, the argument for the log, has to be strictly positive. It has to be strictly positive. Now, later on, we will do this thing. Let me just do it now. Okay, so if we compare exponential function y equals to a to the x, that's for a positive and not 1. If we compare y equals to a to the x and y equals to log base a of x, we know that they are inverse to each other. Okay, so the domain of exponential function is all real numbers. Okay, that will later on be the range of the log function. So the log of log function is all real number as well. while the range of exponential function a to the x is from 0 to infinity. That will be the domain of the log function. Okay, we can go even further, saying that for a to the x, the y-intercept is 0, 1, right? Now that later on will become the x-intercept. The x-intercept for log function, log base a of x, is 1, 0. For exponential function, we don't have x-intercept. A to the x, no x-intercept. Now, when you swap x and y, then that x-intercept will become the y-intercept in log function. Okay, the horizontal asymptote that we have, y equals to 0, later on will become vertical asymptote in log function, x equals 0. Okay, basically their graph are reflections with respect to y equals to x line. Okay, but we'll go into that detail later on. What we pick from here is especially that the domain of log function is strictly positive number. Okay. Under no situation that the argument of log function, okay, the thing that you write after that log, but not the base, has to be strictly positive. Okay, so let's see. For example, we do number 26. Log, actually natural log. Natural log of x squared equals to natural log of 12 minus x. Solve. We already have log with the same base, both of them base e here. Okay, so by one-to-oneness, we can say x squared equals to 12 minus x. Then we solve that. That's a quadratic equation, right? So we get x plus 4, x minus 3 equals 0. We end up with x equals to negative 4, x equals to 3. Then you visually check against the, just visually check. So let me write it down, visual check. So you don't need to show that though. You don't need to show that. Visual check is when x equals to negative 4 is x squared positive. Negative 4 squared is 16, that's positive. And 12 minus negative 4, that's also 16, that's positive. Okay, so x equals negative 4 is okay. How about when x equals to 3? When x equals to 3, 3 squared of course is positive. And 12 minus 3 is also positive. Okay, so both solutions are okay. If you find any solution that is not, that becomes negative, that makes the argument becomes negative, then you need to cancel it. For example, number 24. Number 24, we have log base 7. Log base 7 of x minus 5 equals to log base 7 of 6x. Okay, by one-to-oneness, then x minus 5 equals to 6x. So negative 5 equals to 5x. X equals to negative 1. Okay, now then we do visual check. So you don't need to show this red one here. You can, but you don't need to. It's not part of, it's not like when you square both sides, you need to formally show the checking. Right now, you just need to make sure that this x equals to -1 here. When you plug that into both of the argument, it doesn't make it negative. And if it makes it negative, then you have to cancel that solution. So you have to cancel it and say therefore in this case, so no solution. Okay, now other than this, is actually quite simple. Like question number, let's see, number 28. So far, if we have log equation, that's still a simple one. Number 28, log base 2 of x minus 5 equals to 4. Okay, now notice that this is logarithmic form, so I change it to exponential form. X minus 5 equals to 2 to the 4. So x minus 5 equals to 16, x equals to 21. And visually, 21 minus 5 in that argument will be positive. So we are fine with this answer, don't cancel it. Okay, just like that, actually. Okay, let's see number 34. Number 34, we have e to the negative ln x equals to 0.2. Then what I will do is I change it into, this is exponential form, right? Exponential form. This guy to this guy equals this guy. So I will change it into logarithmic form. Log base e, so ln, of 0.2 equals to negative ln x. Is it okay? So negative ln 0.2 equals to x. Oh, I'm sorry, equals to ln x. Equals to ln x. And you will see this is actually ln of 0.2 to the power of -1. I didn't teach you that. At least I didn't review with that with you. So at least now then we get x equals to 0.2 to the power of -1. That's 1 over 0.2. That's equals to 5. I don't like this because I don't like this solution because there's one little step I didn't explain yet. So I don't expect the textbook wanted you to solve it this way. So what is the other way then? What is the other way that is more acceptable? We rewrite this into e to the ln x to the power of -1 equals to 0.2. So I basically see that negative ln x as -1 times ln x. And we have an exponential property, x to the, not to x, use something else, a to x y equals to a to the xy, right? So I can write it that way. Okay, so e to the ln x is basically x. So x to the -1 equals to 0.2. So x is the reciprocal. That's equals to 5. Okay, I think that's a better solution for this time. Now, using the same trick, I believe we can apply that to number 36. But that's the trick is very similar. E to the x ln 2 equals to 0.25. Okay, I will rewrite it this way. I will rewrite it as e to the ln 2 to the x equals to 0.5. So e to the ln 2 is 2, while 0.25 is 1/4. It's 2 to the power negative 2. That's how we get x equals to negative 2. Okay. Now, next, how about the graph? Like what we said earlier, that the graph of log function and exponential function will be with the reflection with respect to y equals to x line. So let's say, for example, we take a look on let fx be 2 to the x. That's a function that we have seen many times yesterday. And the inverse of that is gx log base 2 of x. Now, what I want to teach you now is that the way we graph this gx function, log base 2 of x, is actually by imagining first the graph of 2 to the x and reflect that with respect to y equals to x line. Okay, that's the plan. So let's see. Trying to get my graphing tape. Let's see, this is our graphing paper. Okay, maybe I enlarged that a little bit. Okay, now 2 to the x is 2 to the x is something we have done yesterday. The y-intercept is 0, 1. When we move one into the right, we double it because the base is 2. Go to the right again, we double it. Go to the right again, we double it, right? And when we go to the left, we half it, we half it. So the graph of this 2 to the x is approximately something like this. And we have the horizontal asymptote on the left-hand side, right? Now then, what I said was that when you want to graph the inverse function, you actually reflect that red graph, which is the exponential function, with respect to this line, y equals to x line. Okay, you reflect that with respect to y equals to x line. Then what happened is, you see the x in the y-intercept 0, 1 becomes 1, 0, 1, 2 becomes 2, 1, negative 1, 1/2 becomes 1/2, negative 1. Basically, it will look like that. Okay, these are the corresponding coordinates from what I had earlier. Pictorially, I get this from here. Reflect, 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 reflect. You can see that as if we are swapping the x and the y. Negative 1, 1/2 becomes 1/2, negative 1. Negative 2, 1/4 becomes 1/4, negative 2. Okay, now then I will connect the dots. So it will look approximately. Now I hope that confirms a couple of things. That the range will be all real numbers. It's from negative infinity goes indefinitely far to the bottom, and it will go indefinitely far to the right. Okay. It also confirms that we have vertical asymptote x equals to 0, which is the y-axis. Okay. I hope that confirm what we learned earlier here. Okay. Now, we have done this thing. We have done this thing. Fx equals to 2 to the x plus 3 minus 4. Okay, there are two ways to work on this problem, but I prefer to see this function here, the log function, not the exponential function. I prefer to see this from transformation point of view. So more or less, it would be nice if you can memorize the graph of log base anything, in this case, log base 2 of x. Okay. Get this, especially these three important coordinates here. Especially those three important coordinates. Okay, now then, so what happened with, so consequently, if I call this example 1, then you call this example 2, what happened if I have the graph, let fx equals to log base 2 of x plus 4 minus 3. Then the graph will be as the following. I basically use the graph that we had earlier, but we move it 3 units to the left and 4 units, no, 4 units to the left, and then yeah, I need to move it 4 units to the left and then 3 units down. So originally, my x-intercept is 1, 0, move 4 units to the left, 3 units down. So it becomes here. Okay. From this 1, 0, 4 to the left, 3 down. Okay. And 2, 1. Move 4 units to the left, 3 down. 1/2, 0, 4 to the left, 3 down. Okay, we have those three important points. If you can get more, that would be great. Like we know that we have 4, 2, so 4 to the left, 3 down will be here. Oh, so computationally later on, we will see that our y-intercept will be 0, -1. Okay, and then we have actually 8, 3, so 4 to the left, 3 down. Oh, that will be our x-intercept. Okay, and then the vertical asymptote, originally the vertical asymptote, the vertical asymptote is x equals to 0, right? That's the original vertical asymptote. Okay, move it 4 units to the left, then the vertical asymptote later on will be here. Okay, let me draw the vertical asymptote. The vertical asymptote will be this is the vertical asymptote x equals to -4, and therefore the graph when I connect the dots will be like this. Okay, but the fact that the x-intercept is 4, 0 and the y-intercept is 0, -1 is something you're supposed to work out analytically. So let's do that problem now. Let's do that problem. then you copy the question here that fx equals to log base 2 of x plus 4 minus 3. So the first question, what's the domain? So you see every function I give you, you need to be able to tell me what's the domain. Okay? And we know the argument of a log has to be strictly positive. Okay, so the domain will be -4 to infinity. And you can confirm that from the graph, right? Okay, how about the range? The range of log function is the domain of exponential function. It's all real numbers. Okay, now how about the y-intercept? The y-intercept, or plug in x equals to 0. So we get log base 2 of 4 minus 3. Now log base 2 of 4 is, you ask yourself, 2 to what power equals 4? Okay, that's how you get the 2, right? Okay, 2 to squared equals to 4. So 2 minus 3 is -1. So the y-intercept is 0, -1. D, how about the x-intercept? You set the function, the value of the function to be 0 and solve for x. So 0 equals to log base 2 of x plus 4 minus 3. So 3 equals to log base 2 of x plus 4. That's 2 to the power of 3 equals to x plus 4. I make it into exponential form. So that's 8 minus 4 equals to x. So x equals to 4. X-intercept is 4, 0. Again, we're supposed to do this ABCD first before doing the graphing. Okay, but since we did the graphing by transformation earlier, then you can see what we did in ABCD here, basically confirm our intuition that helped us graphing the graph the function earlier. Okay, now finally part E, let me write it here. How about the vertical asymptote? You will see the vertical asymptote is the place when the argument becomes 0. Okay, when the argument becomes 0. Okay, when the argument becomes 0. So that's x plus 4 equals to 0, x equals to -4. Okay, so that's about the transformation. I don't think I will need to give you more examples. I just need you to memorize, okay, log base 2 of x looks like what? Log base 3 of x looks like what? Now, once you know log base 3 of x, what log base 3 of x look like, log base 3 of x looks like, then you can work on the transform function. Log base 3 of x plus 7 minus 4. Maybe maybe -2. So if you try to graph it at home later on. So basically, for you to find the graph of log base 3 of x, you need to first know what will the graph of 3 to the x look like. So 3 to the x is an increasing function with increasing exponential function base 3. Okay, so when you do the log base 3 of x, it will be something like this. Okay, now then you move 7 units to the left. Okay, and then you move 2 units down. Okay, with vertical asymptote now, x equals to -7. But that's just a sketch though, that's just a sketch. Okay, suppose, let me just use this example here. Suppose I want to, let me just come from here. Suppose I want to just play with this. Let, for example 3, let fx equals to log base 3 of x plus 7 minus 2. And what is the domain? The domain is from -7 to infinity, not including -7. Because remember, the domain of log base 3 of x, the domain is from 0 to infinity, right? Not including 0. And what happened is, from this guy here to this guy, you move 7 units to the left. Okay. Now, another way to look at that is you say x plus 7 should be greater than 0. So x should be greater than -7. That's another way to look at that. Now, this second method is useful later on if the argument is not linear. Okay, now the range, let me finish this part first. The range will be all real numbers. Okay, as long as your domain gives you the argument from 0 to infinity, then the range will be all real numbers. Now, part 3, how about the y-intercept? The y-intercept will be f0. That's log base 3 of 7 minus 2. Now, the thing is, how do we compute this using our calculator to get a good approximation? It's supposed to be 0, so 0, log base 3 of 7 minus 2. Now, in decimal, what will that be? Okay, now let me find my calculator. Again, you will use scientific calculator, not graphing calculator. But to do the log function, it will be the same. Okay, let me teach you how to use our calculator first. Let me teach you how to use our calculator first. I wonder if our textbook actually teach that part. Yeah, our textbook does not teach us how to use calculator for this. So I have to teach you separately. Now, here's the thing. We need to call, maybe I say it this way, our calculators almost all of our calculators have only log base 10 or natural log. Not log base 3, not log base 2. So if we have log with other bases other than 10 or base e, we need to do some adjustment. And let me borrow from what we're supposed to see in 4.5, change of base. So one of the big reasons you need to learn change of base is so that at least you can compute using your calculator. Okay, now the rule is log base a of x is equal to log base p of x over log base p of a for any p positive and not 1. Okay, so if you have x here and then the base is a, and then the base is a, Now then you can have log base p of a at the bottom, log base p of x at the top. Now this p can be anything, and because of that flexibility, then you can use base 10 or base e. You can use log x over log a, which will always be the same to natural log of x over natural log of a. Now, natural log of a and log base 10 of a are different. They are different, but this ratio will always be the same. This ratio will always be the same. Now then, why do I tell you this? Because if I need to compute log base 3 of 7, I can use log 7 over log 3 or natural log 7 over natural log 3. Either one will give you the same value. Okay, now let me show you the calculator. Okay, let me use natural log 7. Now the thing is, this is still in the parentheses. I need to close it and then divide. Okay, remember to close that 7. Okay, so that's the log for the top, divided by the log at the bottom, natural log of 3 at the bottom, close it. And then I think I need to minus 2. Minus 2, that will be negative 0.22876. Negative 0.22876. That's the approximation in 5 decimal places. Okay, so to compute this is the exact, we say this is the exact solution. This is the exact solution. And when you use calculator, that's the approximate solution. We call that approximate because this number is actually rounded from a longer decimal. Okay, that's the approximate solution. Now that's for how to use calculator. We will bump into that again later. But let me go back to our note. Part D, how about the x-intercept? X-intercept, the y is 0. That's log base 3 of 7 minus 2. So this is 2 equals to, oh, I'm sorry. I think I missed something. So it should be x plus 7, huh? X plus 7 minus 2. So move the 2 to the other side. Change it to exponential form. And we happen to get a nice solution here. So the x-intercept is 2, 0. Now how about the vertical asymptote? Vertical asymptote, x equals to negative 7. Okay, now I don't graph it, but you can graph it yourself later on with using these informations. Okay, using these informations. Don't forget, when you graph it, you need to include those 3 important coordinates near where the bending is the most significant. Okay. From here, I want to go on to 2 small topics. Now, I don't want to call this small because it's actually not that small. For me, these are important. Remember that the domain, remember that the domain of log base A of blah is the set of all x where blah is strictly positive, cannot even be zero. Now, you remember somewhere in the past one of your homework question is finding the domain of square root something, right? Okay, now we can change that problem into, for example, find the domain, and the work will be very, very similar. Actually, I should say it's the same work, but of course the final answer may be different, because under square root, it is okay to be equal to 0. Under log, has to be strictly positive, cannot be equal to 0. So let's say I have log base y equals to log base 3 of x squared minus 5x minus 6 over x squared minus 1. Find the domain. So what I will do first is identify that my x squared minus 5x minus 6 over x squared minus 1 has to be strictly positive, cannot even be 0. And then, oh, it's factorable. So x minus 6, x plus 1 over x plus 1, x minus 1. Do not cancel this x plus 1 though. Do not cancel them. Do not cancel them. Okay, because x equals to -1 clearly is not the domain of this rational function. Not to say that, because it's not the domain of this rational function, then it won't be the domain of the log of that rational function. Okay, so then step 1, we start the procedure then. Step 1, critical numbers are -1, 1, and 6. Cool. Sign graph. -1, 1, and 6. This will be 0 here. This will be undefined here. This will be 0 and undefined, so I use undefined. The sign graph, it will be positive, negative, positive, positive. Because x equals to -1 is a 0 with multiplicity of 2. Why? It happens twice. Once at the top and once at the bottom. Okay, once at the top, once at the bottom. That's why the multiplicity is 2. It happens twice, once at the top, once at the bottom. Therefore, to the right and to the left of that critical number, there should be no change of sign. Then, step 3. We need the positive part. So, -infinity to -1, union, -1 to 1, union, 6 to infinity. Okay, therefore that's the domain. So the domain is this guy. Now, actually, a follow-up question. How about the vertical asymptote? Now, vertical asymptote of log function happens when vertical asymptote is when that argument equals to 0. Of course, if the argument is undefined, okay, from that rational function, you will see that will also give us vertical asymptote. union vertical asymptote caused by that guy. Okay, so in this case here, the vertical asymptote will be when x squared minus 5x minus 6 over x squared minus 1, when this is equal to 0, or when x squared minus 5x minus 6 over x squared minus 1 has has vertical asymptote itself. Even so, if you already have vertical asymptote even before you put it into the log, then even after you put it into the log, it will be vertical asymptote. Now then, from here you will see later on the vertical asymptotes are x equals to -1, x equals to 1, and x equals to 6. Basically, those are the critical numbers that we get from step 1. Okay, so you see how nice is the steps 1, 2, 3 that I show you? It has something to do with this. Okay, now it's now past 12. Just a little bit, let me show you the graph of this ugly function. Just to confirm what we get earlier. Okay, just to confirm what we get earlier. And after that, I give you a break. Y equals to on the top x squared minus 5x minus 6 over x squared minus 1. It's not. Okay, at -1 it's not. I'm sorry. At -1 is not. It's actually a whole even in, my bad. This is a whole. I forgot to, yeah, I forgot that. At -1, that's a whole. It's not. This is not. That will be a whole. That will be the whole in the original rational function. So we see, I'm sorry, I was referring to this earlier. I make a correction here. Yeah, that's a whole. That's not, it's not becoming a vertical asymptote. Okay, now the whole, before you put into log function, when you put into log function, it will still be a whole. And you can see that fact in the graph here. You see that we get a whole here. Okay, yeah, let me copy paste this. Into our notes, and then I give myself a break. Yeah, right now it's 12:05. Let's come back at 12:15. Come back at 12:15. But for here, let me point out that you have a whole here. Fix something. So later on, log. Vertical asymptote here, and vertical asymptote 6. And if you compare with the domain, you see that we are actually missing between 1 to 6. We are missing. Okay, but that hole is so small though, we don't really see that here. Okay, let's continue with our break. Let me change it to 12:18. Okay, now this one here I use actually base 10. I didn't make it base 1, base 3. Okay, but base 3 will be having the same, a similar one though. Okay, let's continue. A little topic from this 4.4 that I still need to take care, just very little. It's about how to solve using calculator some log equations. Like for example, number 56. Number 56, part A. Solve for x. Log x equals to 1.8965. To solve that, this is log form, change it into exponential form, right? And x equals to 10 to the power of 1.8965. Then if I use my calculator, it's base 10, and we happen to have base 10. I need to do new share here. Okay, like this. We happen to have base 10 in our calculator. This is base 10 here. Okay. So what I will do is second 10 to the 1.8965. Now, if you don't have that base 10 on your calculator, you can use this wedge here, that's exponent. Okay, so you type the base first, 10 to the 1.8965. That should give you the same answer. Okay, that should give you the same answer. And that will be x equals to 78.79, 5 decimal places. I want 5 decimal places. 524. Okay, our textbook mentions something about 3 significant digits. 3 significant digits. Basically, 3 non-zero numbers. Okay, so if you have 78 point blah 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 blah, I want 5 decimal places. So that's the answer in black is the one you need to give me. But if you want to say what will be the 3 significant digit for that black number, that the number in black, it will be x equals to 78.8. And what they meant by 3 significant digit means 3 non-zero digit. Okay, and if you have 0 in between 2 non-zeros, you still count it as a significant digit. Okay, let's say part B. Part B, we have log x equals to 4.960. So x equals to 10 to the 4.9680. And then you use your calculator. That's 10 to the 4.9680. Boom. So that will be 92,896. It's what? 92,896.63868. 63868. 5 decimal places. That's what I want. Now, however, if you want to make it into 3 significant digit, means x equals to the first non-zero digits or between non-zero digits. Okay, so it will be 9, 2, and then, so only 1, 2, 3, the rest you round. Okay, so 92,900, that's it. Okay, so that's the 3 significant digits. The numbers after that are 0, so they don't count it as significant in the sense that, how to say that? In the sense that that's how they round it. They just want to see 3 important numbers. Okay, now let me jump to part F right away. Part F, natural log of x equals to -5. Now that's base e, right? So x equals to e to the -5, which will be e to the x. We have that here. Okay, that's e to the x. You can also use this e to that power. So let me show you both. E to the x, right? And then -5. The negative, you need to use this negative sign. Not subtraction sign, but this negative sign. Okay, or you use this e. This is base e here to the power of -5. Oh, they look the same. Okay, so 0.00674. 0.00674. Now, it happens that my 5 decimal places is the same to the 3 significant digits. So this x equals to 0.00674. But my reasoning is I have 5 decimal places. Okay, and the answer for that is because of 3 significant digits. They happen to look the same. Okay, now Now that's for this section here. Your suggested homework will be, I think yesterday I asked you to do some problems from here already. I don't remember. But let me ask you to continue suggested homework from here. Suggested homework from this 4.4b is number 21 to number 61. Just do the odd problem. So there are approximately 20 questions you need to do. Well, I don't expect you to do these problems from this 4.4b between today and tomorrow. No, do your test first. Do well with your test tomorrow. Okay, and then during the weekend after the test, then you start working on this suggested homework. Okay, now let me go on to 4.5. 4.5 is on properties of logs. Properties of logarithms. There are some basic properties that I already mentioned yesterday. Basic properties. It's actually only two, but two basic properties. But the first two are actually special cases of the third one. So the first two is actually a special case of the third one. Log base a of 1 is 0. Again, for a is positive and not 1. Log base anything of 1 is 0. Log base anything of the same thing is 1. And in general, log base anything of the same base to n power is equals to n. Okay, now then the fourth one is a to the log base a of n equals to n. Yeah, the proof is basically for each one of these relies on your ability to play between log form, exponential form, log form. Okay, and more or less I actually proved that, showed that to you yesterday. Now, after these three basic properties, after these four basic properties, there are three properties of log that you need to memorize. Okay, there are three properties of log that you need to memorize. I could call that properties. So you need to memorize the basic ones, of course. Okay, but on the top of that, you need to memorize this also. In fact, memorize it in this order. Okay, the same requirement for a positive not equals to 1 and x and y both positives, strictly positive, then I call this property 1 log base a of x times y equals to log base a of x plus log base a of y. Now, I believe if you took algebra 2 or intermediate algebra recently, you must remember that you have seen this formula before. Okay. Now, I'm doing review right now, so I assume you may have forgotten that a little bit. But this fast review is supposed to refresh your mind, especially because you have a weekend to refresh your mind. Okay. Suppose you say, Thomas, I need more refreshment, like I need more detailed explanation about this, then try to take a look on the lecture video in intermediate algebra from my lecture video. Okay, but I will show you very soon after this. So the first one, log of product equals to sum of log. The second property, log of quotient equals to difference of logs. And then the third property is log base A of x to the r is r log base A of x. Basically, you can move the exponent of that argument to the front to be the coefficient of log. Now, let me show you first what I meant by take a look on my lecture video. And you can also find this on YouTube though. Just search properties of logs. Okay, let me go to the browser. Okay, and then you go to arduino.com and go to Arduino. Go to video, lecture video. Okay, and then from there you can see here Math 125 intermediate algebra. If you click that one and then you go to exponential functions, the property of logarithm 10.4. So you can watch that one to review. They will give you a more detailed explanation. I hope. I see here it's only 10 minutes. I see here it's only 10 minutes. So I don't expect too much from there. Yeah, I don't expect too much from there. Let me go back. You may be able to also see from, if you scroll down, there's a elementary and intermediate algebra from East LA College. Okay, we don't have those courses anymore, but I just leave the videos there for exactly this reason. Okay, if you need to review, then you can do that review here. This is 13 minutes, so I assume they give you a more detailed explanation. Okay, but these are basic though. Okay, these are basic. And one more, maybe if you scroll down even to Santa Monica, you are in Santa Monica, so we have that lecture video also. I don't expect them to be different though. Properties of logs. Okay. Well, this is the basic one. What we are going to do right now is basically applying these properties here. Okay, we will be applying these properties. Okay, let me bring it back. Again, if you think my explanation is not enough, then you can watch more examples from there. Okay, yeah, but I myself will, of course I will do examples too, but I will focus more on the proving. I will focus more on the proofing. Second, close that. Yeah, I will focus more on the proofing here. Even though I don't, in my pre-calculus class, I don't ask you to prove the algebra part. Okay, there will be some proofing later on for trigonometry part, but at least I show you how to do proofing. Okay, at least I show you how to do proofing. So for example, yesterday we have proven, for example, number 3, right? Well, actually I did prove all 4, but let's review that a little bit. Suppose they ask you, for example, prove that log base a of a to the n equals to n. And the way we do it, one way to do it is prove, you say let x equals to log base a of a to the n. Then I will need to show x equals to n. Okay, I will need to show in some math journal, you may see this notation NTS. That's need to show that x equals to n. Okay, so let's call that x first, and then we prove that x is equals to n. Now then, that's a log form. The exponential form will be a to the n equals to a to the x. And then that's the log form. I'm sorry, the exponential form. And then from there, we use one-to-oneness to say that n equals to x. Right? So, by substitution, log base a of a to the n, which is supposed to be equals to x, now we can say it's equals to n. Okay, so that's for that proof number 3. Now, how about the properties that we have above? How do we prove? Now, don't worry, I will not asking you proofing for the algebra part. We will have proofing for the geometry part. I'm sorry, for trigonometry part. Prove property number 1, that is for a, x, and y positive, a is not equals to 1. We have log base a of xy equals to log base a of x plus log base a of y. Okay, and the proof, I will start with let me call something. Let p equals to log base a of x and q be log base a of y. Okay. Let's call it that way first. Now then, that's a log form. So I change each of them into exponential form. A to the p equals to x. A to the p equals to x. A to the q also is equals to y. Right? That's a consequence. Basically, rewrite them into exponential form. Now then, x times y, therefore, equals to a to the p times a to the q. Right? But a to the p times a to the q using product rule of common base, that's a to the p plus q. Right? Now this is exponential form, by the way. Change it to log form. Change it to log form. Then log base a of x times y equals to p plus q, which then consequently, if I substitute that pq back to what I let that to be at the originally, there will be log base a of x plus log base a of y. Therefore, that's the end of the proof. Okay. For part 2 and part 3, you can also see the proof in our textbook, but it's more or less following what I did here. Okay, I don't want to spend too much time in the proof anymore. I need to go into using these formulas, and how to use this to solve equation later on. I was planning to do up to 4.6 today, but I think I don't have enough time for that. Yeah. Let's use those properties. Go to exercises. Let's say we will do question number 2 from this 4.5. So number 2 is good. Yeah, number 2 first, and then after that I do number 4. Number 2. The question is expressed in terms of actually sum or difference of logs of the variable x, y, z, or w. That's from the question. Okay, now then, part A, log base 3 of x, y, z. Of course, the assumption is x, y, z are all positive. Now, this is equal to log base 3. You can see this as x times yz. So this is log x plus log base 3 of yz. Okay, and I go on further. This is equals to log base 3 of x plus log base 3 of y plus log base 3 of z. Okay, so first I see it as this guy with this guy separated. Maybe I use highlight instead. This guy and yc separated. The operation inside that argument is multiplication. So when I split it, it becomes sum of logs. Okay, that's for part A. Part B. Part B, let me do it here. Log base 3 of xz over y. xz over y. So I will see this as numerator, denominator. Okay. That is, I use property number 2, that's log base 3 of xz minus log base 3 of y. And then from there, this is, I use property number 1, log base 3 of x plus log base 3 of z minus log base 3 of y. Now, I go over slower, even though you may think this is fast. I actually go over slower than supposedly because I want you to see how it actually works. Now, after you get used to the mechanism, then we will go a lot faster later on. Okay, I mean a lot faster. Okay, log base 3 of fifth root of y. Fifth root of y equals to log base 3 of y to the 1/5. And using property number 3, that's 1/5 log base 3 of y. That's Mickey Mouse. Okay, that's for number 2. I think that should be quite basic. Number 4. Number 4, log base a of y to the 5th w squared over x to the 4th z cubed. Now I will see this as the top and the bottom, okay? So this is log base a of y to the 5th w squared minus log base a of the denominator x to the 4th z cubed. So I have property number 2 first in this case, because that's log of quotient, right? Log of quotient equals to difference of logs. Then for the first log, that's log of product. Log of product equals to sum of logs. So log base a of y to the 5th plus log base a of w squared minus parentheses log base a of x to the 4th plus log base a of z cubed. Don't forget we have parentheses, right? Okay. Then from there, I use property number 3. I bring the exponent of the argument to the front. So 5 log base a of y, 2 log base a of w, minus 4 log base a of x, minus, let me just use the minus there. Okay. Don't forget that. Log, I'm sorry, 3 log base a c. Okay, now that's where we stop. Now we will come back to this example later on, but let's do one more, number 6. And then we will learn to summarize and do those in one step. Okay, number 6. Number 6, let me do it next door. So consider this like a warming up. Log base 10, because I don't give us the base, square root of y over x to the 4th cube root of z. Just like before, I will see this numerator, denominator. This will be log of square root of y minus log of x to the 4th cube root of z. And then let me rewrite this as log y to the 1/2. Okay, minus parentheses log x to the 4th plus log cube root of z, which is c to the 1/3. Okay, and then I will bring the exponent of the argument to the front, to the coefficient, minus 4 log x minus, because I distributed negative, 1/3 that comes from c to the 1/3 log c. Now, especially from the last two examples, I want you to see a pattern. What kind of pattern? Notice that the coefficient is always the exponent of the base. Okay, that will be positive if it comes from the numerator. So you see this 5 here is the exponent of y to the 5th. This 2 here is the exponent of w squared. Okay, now x to the 4th is on the denominator, so it will be negative coefficient. Okay, and negative 3 here also coming from c cubed on the denominator. So if it comes from a base from the denominator, then the coefficient of that log will be negative of that exponent. Okay, oops, I think I made a mistake here. We should be 1/2 here. We should be 1/2. Yeah, good thing that I go over that again. Now, then in the last example here, you see this is y to the power of 1/2, right? So the 1/2 goes to the front of that y. Okay, and then x to the 4th on the denominator, so you will get negative 4 for the coefficient for log x. And likewise, cube root of c is on the denominator, that's why you have that negative. The cube root means the power of 1/3 with c. Now, suppose for example, I do another example, but I hope we can do it super fast. So basically, if I have log base a of x to the 5th, 4th root of y, and then c to square, and cube root of w squared. We want to express this as the sum and difference of logs of x, y, z, or w. Then let's see, this is x to the 5th on the top. Then that would be 5 log base a of x. 4th root of y is on the top. So that's exponent 1/4. On the top, that's plus log base a of y. And then c squared at the bottom. That's negative 2 log base a of c. And finally, cube root of w squared also at the bottom. So that would be negative 2/3 log base a of w. You see, we do this in one single strike, in one single step. Okay, if you consider this as if you are driving, then this procedure, breaking them up into sum or difference of log, can be associated with driving forward. Now, however, what we need to be able to do is to go backward. So to go backward in the sense that suppose we are given something like this, can we condense them into a single log? Okay, that's actually a more difficult work, but at the same time, if we already know how to go forward, then going backward is something reasonable to do. Okay, something reasonable to learn. If we cannot even drive forward, forget driving backward. Okay, now, so let's go on to another example. Let's say question number 12. And the question is, write as a single log. So we condense that into log of something, okay? Instead of long terms, a lot of parts, we put them together. So we have 5 log base a of x minus 1/2 log base A of 3x minus 4 minus 3 times log base A of 5x plus 1. Now, do it in one single strike whenever possible. This is log base A of, now this is positive 5 with base x, so this is x to the 5th. Okay, now then, so this is positive, right? Then this is the negative part. Because it's negative, it is at the bottom. Because it's negative, it's at the bottom. That will be square root of 3x minus 4. Okay, and then negative 3 means it is at the bottom with base 5x plus 1. So that would be 5x plus 1 cubed. That's what it looks like. Okay, that's for number 12. Number 16. Maybe number 14 first. Number 14 first. Number 14, we have 2 log base 10 here, y cubed over x minus 3 log. Thomas, you show the work in one single step. Is it okay if I show in more than one step? Yes. Yes, it's okay. It's okay if you want to show more steps, but of course, the way you write it has to be correct. Okay? And the way you write it has to be correct. Okay, sometimes you need to slow down and actually break it up a bit further. You know, I think that's the same for this question here. Okay, right now it's almost 1 o'clock. Let me give you a break together with working on this problem. Okay. Together with working on this problem, we come back at, that should take you approximately 2 or 3 minutes. So let's come back at 12:12. I'm sorry, 1:12. Let's try to do this number 14. I think I need to go a bit slower. This is log of y to the 6 over x squared, right? Because I moved the square here to the front, to the top there. And then y cubed squared is y to the 6, x being squared is x squared, minus log y cubed plus log x squared y. Now let's put them together. This is single log of y to the 6 over x squared, y cubed at the bottom because the coefficient is negative, and x squared y on the top because the coefficient is positive. Now let's simplify that a little bit. Oh, the x squared cancel, huh? So I get log y to the 7th over y cubed. That's log y to the 4th. Now, what is the reason we learn these properties? The main reason is to solve logarithmic equations. The main reason, of course, there are other reasons, but for now, the main reason we learn properties of logs is to solve log equations. We have learned to solve some simple log equations earlier in 4.4, but in 4.5, after being equipped with more properties, then we are now ready to do a lot more problems. So I think for the next 30 minutes, I guess, I hope not that much, I will do solving equations. Okay, I will do solving equations. Number 18, log base 4 of 3x plus 2 equals to log base 4 of 7 plus log base 4 of 3. Now, let me give you the big story first, the big story. The big story will be as the following. Okay, there are two possible things can happen. The first one is you have log blah equals to log blade with the same base. Now, if you have the same base and single log on the left, single log on the right, then by one-to-oneness, we need to solve blah equals to blade. Of course, in your final answer, you need to check the domain. Okay, make sure that the solution you have will not make the argument, will not make the blah or blade here to be negative. Okay, second, another possibility is you have log only on one side and the other side is without log. Okay, now if that's the situation, what we do next is we change that into exponential form. So a to the blade equals to blah. Okay, so so if we have logs everywhere, make them into single log on both sides. If we have some constants, then separate the logs on one side, make it single log, and constant on the other side, make it, you will see that as single expression. Okay, now in this case here, you have two logs, sum of logs on the right hand side. So what I will do is I put them together first. That's log base 4 of 7 times 3, right? On the left hand side, it's the same. And then by one-to-oneness, we get 3x plus 2 equals to 21. So 3x is 19, and x is 19 over 3. Okay. Number 22. We have log x plus 2 minus log x equals to 2 log 4. We have log. So on the left hand side, I use property number 2, make it into single log, x plus 2 over x. And the right hand side, I use property number 3, I get log 4 squared. Okay, so x plus 2 over x equals to that 4 squared, which is 16. Then from here we get x plus 2 equals to 16x, 2 equals to 15x, and x equals to 2 over 15. Now visual check. So you do visual check here, you remember x equals to this. This is positive number. When I plug in here, it will be positive, it will still be positive, so we are fine, right? Okay, now how about this here? This number is positive, so when I plus some positive number, we are fine. And that number itself is positive number, so we are fine. Okay, no need to cancel anything. That's for number 22. Now, how about number 24? We have natural log of x plus natural log of x plus 6 equals to 1/2 natural log of 9. On the left hand side, that's sum of logs equals to log of product. On the right-hand side, that's natural log of 9 to the 1/2. Log blah equals log blade means blah equals to blade. Right? Because this is ln3, right? Now that's a quadratic equation. I don't think that's factorable. I don't think this is factorable, but I can just go ahead with completing the square. So I will have x squared plus 6x plus 9 equals to 3 plus 9. Okay, so x plus 3 squared equals to 12. X plus 3 equals to plus minus square root of 12. We did this kind of question before. Okay. In fact, I believe I asked similar question in your test 1. This is 2 square root of 3, so I get x equals to negative 3 plus minus 2 square root of 3. Now, there are two solutions here. The first one is negative 3 plus 2 square root of 3. And x2 is negative 3 minus 2 square root of 3. Okay, now the thing is visually check. Visually check. Notice this guy, you can try to use your calculator. Okay, but I know that's positive. I know that's positive. This is positive. So when I plug that into here, the argument is positive. Into here, it is still positive. Okay, so that one is fine. Okay, this one is fine. However, when I plug this guy, this is negative here, such that when I plug it in here, it becomes log of negative argument. So we have to reject that right away. Okay, we have to reject that right away. Reject that right away. And let me tell you the explanation. Well, because natural log of negative 3 minus 2 square root of 3 is undefined. Okay, basically the argument is negative. So you cross that out. Okay, you cross that out. Okay. Yeah, but Thomas, why do we have extra solutions like that? You know, because if I plug this number in, if I plug this negative number in here, it works. Okay, it will work. Trust me. If you plug in there, it will work. But why it doesn't work in the original problem? Why it doesn't work in the original problem? Now, the explanation is as the following. There's a change of domain. There's a change of domain. So consider ln x plus ln x plus 6. Call that a function fx. And compare that with gx, which is natural log of x times x plus 6. Okay, now the domain of gx, when we combine them into single log, turns out to be larger because x times x plus 6 needs to be positive, right? So the critical number will be 0 and negative 6. When we do the sign graph, this is 0, I'm sorry, this is negative 6, this is 0, this is positive, negative, positive. So the solution for that inequality is from negative infinity to 0, union, to negative 6, and then union 0 to infinity. So that's the domain. Negative infinity to negative 6, union 0 to infinity. That's the domain. Okay. However, on the left-hand side, when you look at the domain, notice that x has to be positive and x has to be, x plus 6 has to be positive. So x has to be greater than 0 and x has to be greater than -6. So it has to be greater than 0 and also greater than -6. Oh, sorry. I should not use bracket. I should use parentheses. 0 and -6. And it has to satisfy both of them. It has to satisfy these and also satisfy these. So you see the one double shaded will be the domain. That's from 0 to infinity only. Okay, so what happened is when we combine those two logs, this sum of two logs, and we change it into a single log, okay, we what you call that, unintentionally, okay, we need to realize that even though they are equal, that's only if both of the factors are positive. Only if both of these are positive. Now notice that if this guy is positive, this guy is positive, the product is positive, right? Okay. But it is possible that x is negative and x plus 6 also negative, and therefore it's not in the domain of this fx. However, the product of negative and negative is positive, and suddenly it becomes in the domain of gx. Okay, so in other words, by combining them together, we need to realize that we actually make the domain larger. Therefore, we may have extraneous solution that is not in the original equation. That's why we need to do that check. Okay, so the key situation is this. The key situation is this. What happened there is you have the situation where ln negative plus ln negative, which is supposed to be not in the domain, so that's undefined, supposed to be. But when you use property number 1, it becomes log negative times negative, which is log positive. And suddenly it is well defined. Okay, so it happens with the question mark where the assumption is that the domain, okay, the argument has to be positive, which when you put them together, the product, if both of them negative, the product becomes positive. Suddenly it seems to be workable while it's actually not. Okay, while it's actually not. So maybe I say this, okay, to contrast that using a more concrete example. Okay, to contrast that using a more concrete example, let fx equals to log of x plus 6 plus log x minus 4. Maybe I use x plus 6 and x plus 4, or x minus 6, x minus 6 and x minus 4. X minus 6, x minus 4. Okay, now when you argue that this is equals to gx, which is log of x minus 6, x minus 4, you need to be aware that this is only true. This is only true if x minus 6 is greater than 0 and x minus 4 is greater than 0. Okay, now the thing is, sometimes when we say they are equal, we don't realize that there's some requirement, there's some assumption need to be satisfied before we put them together. Okay, the way we do it will be we just put them together first and then we check at the end if it satisfies the requirement. Okay, but notice that gx gx has y-intercept. Go try. G0 is equals to log of 24, right? Okay, so the y-intercept is 0, comma, log 24. But this guy, fx here, it doesn't have y-intercept. No y-intercept. Why? Because x equals to 0 is not in the domain. Right? You will get log -6 plus log -4. But log -6 is undefined. Log -4 also undefined. Okay? I hope that really contrasts that these two functions, they are only the same under some situation. Okay, they're only the same under some situation. Okay, now let me do more problems. For example, number 28. Which one I did? I did number 24. I think number 28 is very similar. Let's do number 30. Number 30. Log base 3 of x minus 2 plus log base 3 of x minus 4 equals to 2. So you have two logs on one side and one term without log on the other side. So that's already separated. Let's put them together. So that will be log of x minus 2 times x minus 4 in single log equals to 2. Okay, so this is log base 3 of x squared minus 6x plus 8 equals to 2. Then change it into exponential form. X squared minus 6x plus 8 equals to 3 squared, which is 9. So x squared minus 6x equals to 1. I will proceed with completing the square here. X minus 3 squared equals to 10. So x minus 3 is plus minus square root of 10. X is 3 plus minus square root of 10. Now don't forget the reason that in the past I told you to always split that is because of what we actually see right now. There are two solutions there, not only one, two solutions. There are two solutions there. Okay, now notice that the first part is already positive. This part here is already positive. Okay, it's greater than 2, right? So when I plug into x minus 2, that will still be positive. And this is 10 is more than 1. It's actually 3 point something. Right? If I do a rough estimate, this is 3 plus 3 point something. Okay, so this will be at least 6, but of course no more than 7. Okay, now 6 minus 2 is positive. Okay, 6 minus 4 is still positive. So either way, when I plug that into the equation, it will be defined in the domain. Okay, so again, I just do visual check. This is okay. Now the problem is this guy is not. Okay, 3 is less than square root of 10 because 3 is square root of 9, right? So 3 minus square root of 10 is definitely negative. Now when you subtract by 2, when we subtract a negative number by 2, it will be even more negative, right? Okay, so 3 minus square root of 10 minus 2 will be 1 minus square root of 10. It will still be negative, right? And that's the reason I will cross this solution out. Okay, only one solution works. Last example from here. Last example from here, number 38. I do the hardest possible questions. I hope it makes you happy that I do enough examples. And therefore you have no reasons to say, Thomas, I need more examples. No. Actually, if you think about it, there's actually, when you do math, you don't need to do a lot of examples. You need to do enough examples in the lectures and a lot of exercises, right? Okay, but what what is more important is for each of that example, you don't need a lot, but for each of that examples, you actually understand from one step to the next step. Okay, that's why I'm not really into telling you that, you know what, you need to skip all the steps, so on and so forth. No, actually, no, that's not the reason. Okay, you need to be able to show the reasoning behind it. So log base 2 of x plus 3 equals to log base 2 of x minus 3 plus log base 3 of 9 plus 4 log base 4 of 3. Oh, seems like we need to simplify first. This will be constant here. This will give us a constant here. This also will give us a constant. Let me just compute them. And I will move this guy to the left. Okay, so I get log base 2 of x plus 3 minus log base 2 of x minus 3. Later on, I will make them into a single log. Okay, now how about log base 3 of 9? Log base 3 of 9 is log base 3 of 3 squared, right? 3 to what power equals to 9? That's 2. Okay. Plus, how about log, I'm sorry, 4 to the log base 4 of 3. What's that? Well, I don't know what's that, but let me call that y. I don't want to call that x because I don't want to confuse with the other x that we already have. Let me call that y. Now then, if I change it into log form, log base 4 of y equals to log base 4 of 3. Oh, by one-to-oneness, then y equals to 3. Okay, by the way, that's basic property number 4. That's basic property number 4. This is 3. Now then, on the left-hand side, we have difference of logs. That's log base 2 of quotient equals to 5. Oh, Thomas, what should I do from here? Well, you have log on one side, and you have constant on the other side. I mean, without log on the other side, to be more precise. Then I will change it into exponential form. Okay, and then that's x plus 3 over x minus 3 equals to 32. So x plus 3 equals to 32 times x minus 3. So x plus 3 equals to 32x minus 6. So that will be 99 equals to 31x. X is 99 over 31. Now we need to do checking, make sure that it is actually okay in the domain. And what we need is this number to be greater than -3. So x plus 3 has to be greater than 0. X minus 3 also has to be greater than 0, which means s has to be greater than -3 and x has to be greater than 3. That's all we need, right? But I believe this 99 over 31 is more than 3. This is actually 90, that's 93 plus 6, right, on the top. So that's 93 plus 6 over 31. So that's 3 and 6 over 31. That's greater than 3. Okay, supposed to use red color there. This is greater than 3. Okay, so we are checked. That's the answer. That makes all the argument to be positive. Now, suggested homework from here. Suggested homework from here from 4.5 will be number 1 to number 37. Again, don't do it today. Do it tomorrow during the break, during the weekend. Okay, after the test, then you do the test. I mean the homework. 4.6. So, of course, I need you to study during the weekend. Okay, after the test, don't slack off. This class is super fast. This is 6 weeks covering something supposed to be fast, even in 15 weeks. Okay, 4.6. 4.6 is on exponential. Exponential and logarithmic equation. They're basically more things put together. Okay, let's do some simple one first. So here in this section, we'll do examples only. Okay, but the first one, suppose, for example, we want to solve, let's say I have 7 to the x equals to 21. No, the answer is not 3. The answer is not 3 because 7 cubed is not 21. Okay, don't confuse that with 7 times 3. Okay, now then how do we solve these times? 21, the way we solved that before, we changed 21 into base 7. Okay, but 21 is not a base 7 number. So what should I do? Change it into log form. So log base 7 of 21 equals to x. And then you use calculator where you'd apply change of base first. Let me use base 10. They call it common log, the common base. Okay, then you use your calculator. Log 21 over log 7. No, the log don't cancel. No. Okay, the log don't cancel when you use your calculator. So log base 7 of 21 is the exact solution, but for us to compute the approximate solution, then we use calculate log 21. Don't forget to close the parentheses divided by log 7. Okay, now, or you can also use natural log, natural log of 21 divided by natural log of 7. Okay, you see they're the same. Okay, so both of them logs or both of them natural log. You cannot use one of them common log and the other one natural log. No. Both of them base 10 or both of them base e. Okay, and again that would be 1.56458. So x equals to 1.56458. Is it what we're supposed to do? Yep, when we round to 5 decimal places. A more difficult case. This will be the last example I do for the day, and on Monday I'll continue a bit more from here. Actually, there will be around 1 hour to finish these sections from here. because there are interesting problems actually from this section. Number 2, example 2, is the situation where we have exponential function with different base on both sides. Let's say if I have number 18, I just quoted from the book. We have 3 to the 2 minus 3x equals to 4 to the 2x plus 1. Now, this problem can be done using 4 different bases. So you have more than one way, actually, at least 4 ways to do that. Okay. Either you use base 3 or base 4 or base 10 or base E. Now, I will show you 2 of them. The other 2 you can try. But whichever method you use, base 3, base 4, base E, base 10, it will be the same. The final answer will be the same. Okay, so we do have choices here. Let's say, for example, I choose to use base 3. Okay, so I apply log base 3 to both sides. Okay, I apply log base 3 to both sides. And you will see on the left-hand side, it will be the exponent goes to the coefficient, right? Don't forget the parentheses though. Exponent goes to the coefficient. So this will be log base 3 of 3 is just 1. So 2 minus 3x equals to 2x plus 1 times log base 3 of 4. Okay. By the way, I want you to realize that we can do it even faster if you simply look at that problem in the following way. This is the base, this is the exponent, and this is the argument. Okay, so you can see that this is log base 3 of 4 to the power of 2x plus 1 equals to the exponent 2 minus 3x. And I move the 2x plus 1 to the front. That's what we get, right? So it is actually the same to the other method that we did earlier, the one here, the same to what we did here. Okay, but that method is faster. So it's not really saying that we apply log base 3 to both sides. You can say it that way because log base 3 is a one-to-one function. So yes, we can see it that way. But I think we can also see it as like we simply change that into logarithmic form. Now, when you write it in log form, you can choose base 3 or base 4. Depends on which one you like more or which one you like less. Doesn't matter. Okay? Yeah, so you see that these two are equivalent. I will just go on with one of them. They're the same anyway. Okay? I need to solve for x. So 2 minus 3x. I will distribute the one on the right-hand side here. 2x log 4 base 3 of 4 plus log base 3 of 4. My purpose is I will collect those x's terms to the same side and the ones without x terms to the other side. Why do you do that, Thomas? So that I can factor the x. 2 log base 3 of 4 plus 3. Okay, so x is now equals to 2 minus log base 3 of 4 over 2 log base 3 of 4 plus 3. Now, this is what we call exact solution. This is the exact solution. Okay. Now, if you use base 4, they may look a bit different. Okay, but when you compute the approximate solution, then the approximate solution will give you the same number. Okay. Now, let's see. Suppose I want to compute this. I need to do change of base first. Log 4 over log 3 big over log 16, the 2 to the 4, you bring the 2 to the front. I mean to the exponent, right? You bring these 2 here to the exponent. Okay. That will be log 16 over log 3 plus 3. And then I will multiply the top and the bottom by the LCD log 3 so that I can polish that, make it look nicer, right? So I get x equals to 2 log 3 minus log 4 over log 16 plus 3 log 3. Now then, from here you can use calculator. Okay, from here you can use calculator. But I think if you don't want to be hassled too much with your calculator, okay, this is still exact solution, by the way. This is still exact solution. This is still exact solution. Okay, and you can use calculator already from there. But if I were you, I will simplify that a little bit further. Okay, I make it like this. This is log 3 squared, right? Minus log 4. And this is log 16 plus log 3 cubed. So this is log 9 over log 4. I'm sorry, log 9 over 4. Big over log 16 times 0.7. Then from there you use your calculator. Then from there you use your calculator. So on the top I get log 9 over 4 close parentheses divided by log 16 times 3 cubed, or if you know 3 cubed is 0.7, go ahead. The answer is 0.133 something. 13363. Okay. Now, suppose, for example, you don't want to simplify that and you say, you know what, let me just hit it right away from there. It's already simple enough, already with common log base 10 or natural log base e, and you want to punch it in right away, go ahead. Yeah, you can do that too. You can do that too. But a lot of parentheses should be used. So parentheses, see, I have some terms on the numerator and some terms on the denominator. So I need to use parentheses. Okay? The numerator term, 2 log 3, make sure you close that 3, minus log 4, make sure you close that 4, and then you close the numerator. Divided by the grouping at the bottom. Okay, the grouping at the bottom, log 16, close the 16, plus 3 times log 3. Oops, not 6, 3. close the tree, and then close the grouping on the denominator. So what the parentheses are. Okay, so you see that we get the same answer, right? Same answer. Okay, suggested homework from here. Again, I don't want you to do this 4.4b to 4.6a between today and tomorrow. Do it during the break, during the weekend. Okay, but I would like you to do number 1 to number, let's see, which question. I think you can do up to number 24 or 23 already. Number 1 to number 23. Do the option. Okay. Now, I will stop the recording now. I will stop the recording now, but then I have another recording right after this, what to expect when you do tomorrow, when you do the test. I assume you already know what to do in regards of printing your test out and then scanning it. Either you use a cam scanner or you actually scan it using some scanner and convert that to PDF and then upload it to Canvas. Okay, the new stuff that you will see tomorrow is that you need to be online and you need to show me your ID, and you need to be able to have your head, your hands, and your desk visible at all time. Okay, now, so let me stop the recording now.